theorem 1.2. Theorem 1.1 was representation theorem. Okay, let X be locally compact. Sigma compact Hausdorff space. Let mu be a measure on sigma algebra M in X, representing a bounded linear functional, representing a, positive linear functional, representing a positive linear functional as in Rie's representation theorem. Then we have the following properties. Then the following properties. Property A, if E is a member of sigma algebra and epsilon is greater than 0, then there is a closed set F and an open set say V such that F is contained in E is contained in V, and mu of V minus epsilon is very, very small, and mu of V minus F is less than epsilon. Second property, mu is a regular Borel measure on X. Yesterday we discussed regular Borel means it is irregular and outer regular. Third property, see, if E belongs to sigma algebra M, then there are sets A and B with A and F sigma set, B G delta set, and A is contained in E is contained in B with mu of P minus A 0. Okay, so you know regular Borel measure. Now we come to F sigma sets and G delta sets. This definition we have done in the course of Major 3, advanced real analysis in second semester. So what I will discuss what you mean by F sigma, and I will recall what you mean by F sigma G delta set. First, as you know, Borel measure, Borel sets. What do you mean of Borel sets? What do you take? Let X be a topological space. Then you know that. Then there exists a smallest sigma algebra V in X such that every open set in X belongs to B. The members of this V are called Borel sets. The members of B are called Borel sets. In X. Now it means open set is a Borel set. The question is whether closed sets are also Borel sets. The closed sets are thus closed sets are also Borel sets, because if A belongs to M, then A implies A complement also belongs to M. Thus all countable union of closed sets and countable intersections of open sets are also Borel sets, because definition of sigma algebra, we are calling this are Borel sets. This first one, countable union of closed sets, this is known as F sigma set. F sigma set. And countable union of intersection of open sets, this is known as G delta sets. G delta sets. Just for example, same in this half open interval, this is a G delta set and F sigma in R. So these are the definitions of G delta and F sigma set. So again we come to proof of this theorem. Let part A, first we prove part A, proof A part. What we are given, X is sigma compact. Since X is sigma compact, and we know then X can be the countable union of compact set. So we have X equal to union I from 1 to infinity Ki. Each Ki is compact. Okay. If E belongs to M sigma algebra and epsilon greater than 0, then mu of ki intersection E is less than or equal to, because K intersection A is contained in ki as well as E, so less than mu of ki, and you know this measure is always finite. You know, you have done in the statement of representation theorem, mu of k is finite for every compact subset K, and this is finite because mu of ki is finite for every compact K. Okay, so epsilon is given since E is autoregular, there exists open sets Vi which contain Ki intersection E such that measure of Vi minus intersection Ki with E, this is less than epsilon. Here epsilon we take less than epsilon by 2 power I plus 1 for I 1, 2, 3, so on. Put this as equation 1. Okay. Put V equal union of these Vi's. I from 1 to infinity. Vi. Okay. Then clearly E is subset of V. And V minus E is contained in union I from 1 to infinity Vi minus Ki intersection. Let's check. E you can write as E intersection Y. E is contained in V. E intersection X. Let's prove it. This is E intersection X, you can write union I from 1 to infinity Ki, and this value is equal to union I from 1 to infinity E intersection Ki. And this is contained in I from 1 to union I from 1 to infinity Vi. Okay, see here, and this value is equal to V, so E is contained. So from there you can, this value is also true. Now therefore measure of V minus E is less than or equal to mu of union I from 1 to infinity Vi minus Ki intersection E, and this is because we use the measure summation I from 1 to infinity mu of Vi minus Ki intersection E, property of measure, and this is the, you have done this value is just less than summation I from 1 to infinity, yes, epsilon upon 2I plus 1, and this value is nothing but epsilon by 2. Geometric series. Okay, this we have done for E in M, and we know that M is a sigma algebra, so complement of E also belongs to M. So we apply the above theorem, applying the above theorem, above argument, argument to E complement in place of E. What do you get? There exists an open set W containing E complement such that mu of W minus E complement is less than epsilon 2. That's just like this. You have done this one. So we conclude here, that's an epsilon 2. Put F equal to W complement. Since W is open, so this complement is closed. So what do you get? Then F is closed. And F you can write as W complement. W, you know, this is contained in E complement. I will write it as contained in complement, and this equal to E. Means F is contained in E. Okay. Also, E, we calculate E minus F. Okay. E, this you can write by set 30 properties. F complement, and this value is equal to E intersection W, and this value equal to E intersection E complement. So this value is, you can write, no sorry, this value, okay, we write it like this. E intersection W, sorry, you can write it like this. Write this one as W. W by definition, this one we did it here. Where? Yes, like this property minus E complement. Okay. So E minus F is equal to W minus E complement. Therefore, measure of E minus F is equal to measure of W minus E complement, and this is less than epsilon 2. See here. Okay. Since, again, set 30 property, since for set 30, V minus F is contained in, you can easily verify it, V minus E union E minus F. We have mu of V minus F is contained in less than equal to, I am contained with the property mu of V minus E plus mu of E minus F. And this is epsilon y to this epsilon y, this is less than epsilon. So what you have done? Thus we get a closed set F. Get a closed set F and an open set and an open set V with property F is contained, E is contained in V, and this, and mu of V minus F is less than epsilon. And this was our proof. This was a part A. Thus, part A is proved. Okay, now we prove part B. Let F be a closed set in X. Since each ki is compact, each ki is compact, since each ki is compact and compact subsets of a Hausdorff space are closed. This you know. It follows that each ki is closed. And so F intersection ki is closed in X. Also, again topological property, also closed subsets of a compact set are compact. You know this in the course of topology you will learn. Compact. Therefore, what do you get? Therefore, F intersection ki is compact for each I. Also, F you can write as F intersection X, F intersection union I from 1 to infinity, ki, and this value is equal to, I from 1 to infinity, F intersection ki. What do you get proved? You are writing F union I from 1 to infinity, F intersection ki. So you are writing F as counted union compact sets. So what closed sets? Correct. Therefore, F you are writing counted union of compact set. Therefore, by definition sigma compact set, what do you get? Therefore, F is sigma compact. Now we write let Fn, we write Fn equal to union I from 1 to n F intersection ki. So what do you see here? We see that means this increasing sequence of curve sets. We see that F is an increasing sequence of f is increasing union of compact sets Fn, because F1 is contained F2, so on. F is an increasing sequence of compact sets Fn, but mu is continuous from below. But mu is continuous from below. Therefore, mu of f is equal to, you can write equal to mu of union n from 1 to infinity Fn, and this value equal to mu of limit n tending to infinity Fn, definition of limit here, minimum limit, and this value is equal to, because mu is lower semi-continuous, continuous from below, limit n from 1, this you can write as mu of Fn, correct? And this value is nothing but equal, because Fn's are increasing sequence, these are supremum and mu of Fn, so that n belongs to, thus we see that every closed set in X, every closed set in X is irregular. Thus, from part A, it follows that every Borel set is irregular. Okay, and we know that outer regularity is granted by the representation theorem, so we get that mu is regular. Okay, so since outer regularity of a Borel set is granted by representation theorem. Because why? Because it is given that mu represents a positive linear functional function, because mu represents a positive linear functional on CCX. Okay. what do you get? Since outer regularity of a Borel set is granted by this penetration theorem, because as we have taken a hypothesis, mu depends a positive linear functional on Cx, CCx. It follows that mu is a regular Borel measure. This is part B. To prove part C, we apply part A with epsilon 1 by k for k equal to 1, 2, 3, so on. So by part A, then there exists a closed set Fk and open sets Vk such that Fk is contained in E is contained Vk is contained in E contained Vk, and mu of Vk minus Fk is less than 1 by less than epsilon means here 1 by k. Put A equals union of these Fk's, union of k from 1 to infinity Fk, and B equal to intersection k from 1 to infinity Vk. Okay. So by definition of G delta set of F sigma sets, when A is F sigma set, then clearly A is an F sigma set and B is a G delta set. Further, and A is contained in E is contained in A with mu of B minus A equal to 0 because B minus A is contained in Vk minus Fk for all k. Okay, you can see from this one. Therefore, mu of P minus A is equal to mu of is less than equal to mu of Vk minus Fk, and this value is less than 1 by k, which goes to 0 as k tends to infinity. Means mu of V minus A is 0. Okay, and this proves the theorem.